Happy New Year. So welcome. Recently I've been looking into something called slime simulation. So I saw this blog about the particular topic, and also this paper. It has a nice paper. I'm not going to open it up right now. So that you can see this blog, you can read it. Now it gives us a simple algorithm, or rather a system, where we are simulating small individuals, small particles or slime, and we are getting these kind of complicated parts. So I was curious, and I also saw a video of Sebastian League on this topic. Well, after that, there was I wanted to try it out. I wanted to try it out, so I made an implementation, something like this. So if I say show it right now, okay, it was something like this. Now you can see it's quite chaotic, and also it can have a lot of behaviors. Okay, now if I can adjust the parameters, like it can create a lot of different shapes and different patterns. Now yeah, this was the basic slime simulation. Now apart from the exact logic from this particular blog, well, I also got the idea from the Sebastian League's video about assigning each and every individual a particular color, rather so which will act as something like a genotype, or it will separate the species out. So, and we can like tweak the simulation in particular way, so to keep that species thing in mind, and we can get this kind of interesting results where you can see a particular species of slime flocking around. Right now, this was one thing. Now I was there like trying to get something more with this done. So recently I just implemented something that would be more interesting with this, that is trying to create paths between points, or rather towns, with this kind of a simulation, right? So let me just show it to you right now. Okay, so I've got this basic simulation right out here. Now this is a particular town. I can move it out with my mouse. This town will have the particles around it. Now the resolution is a bit low because my computer can't really handle too many particles while recording the video, so sorry for that. Now okay, so I've got one town. Let me just explain you what exactly is happening. So I've got this I've got a list of towns. Now each particle is assigned a particular town. Now in the current version, each particle will start at a particular town and have a particular genotype, or a species, or a color. Now if I just add another town out there, you can see there is another town. Now I guess you can guess what is happening out there. The particles are moving from this town to this town and this town. It's circling. If I add another town, you can see particles are moving from this to this, and this back again. It's just rotating or cycling from one town to the other. Now this is not really interesting in that sense, because a lot of yes, we can see a lot of interesting paths and interesting curves without actually programming any logic for any particular curve. It's showing us curves, but well, that's not the most interesting thing yet, right? We can add more curves, we can add more towns, and yeah, it will move from this to this and create complicated paths. Now I can change the simulation parameters. Now what are the simulation parameters? There is something called a sensor length. What is a sensor length? What is a sensor basically? So each particle is moving in a particular direction, right? So we are calculating a particular direction for each particle. So we'll just go in that direction, and like in a particular amount, the length of the sensor, or probe a particular amount of area, and with that we'll just decide we'll probe that area, and we'll decide where to move next. That will be the particle's next direction. So something like that. I'll get to the details a bit later. I'll just open up the code and go to the details, and we'll modify things. Well, a lot of interesting things. Alright, so if I just increase the sensor length, we can see different paths are being formed, and it's quite interesting to see it's forming paths. Also, if I can also increase the sensor angle to increase flocking. Okay, now let's just move aside from these. There is one more thing I want to say, that currently there is only one species of particle out there, because I've not reset the thing. If I just reset, we can see different species of particles that are being out there, as each species has a different color. So you can see each now one more behavior that you might see notice is that same species is trying to cling together, and different species are trying to repel each other. For example, the green particles are trying to, like, there are multiple shades of green, right? One is a dark green, one is a light green. So we just reset it. You can see these three are green particles with different shades. Now these green particles are trying to like attract each other and kind of mixing in, right? But the blue particles or bluish white particles are kind of avoiding that and trying to form flocks among itself. Now the part like I've reduced the like the sensor like particles field of view too much, so if we can, like, it's having some weird behavior. If I just increase it a bit, you'll see we can see beautiful patterns, and it's trying to create flocks and move from one town to the other, right? If I just add more towns, it will be more clear. Now it's going from this, you can see, and the bluish white particle is kind of avoiding it. But again, all the, like, each town has a different starting species, so we can have we are having 5 species right now. If I just increase it to a lot, you can see some really complex behavior, and I can just adjust the positions of these towns. I'm calling them towns, you can call them points, whatever, right? We can see quite intricate behavior out there. Now it's moving from one town to the other, and you can see it's interesting behaviors out there. I can change the behavior by changing the parameters, right? Now it's not like we're getting different kinds of paths for each particular parameter set. For example, if I reduce the sensor length, we can see the particles will start moving in more random ways, because, you know, it will try to sample very close to each itself, and maybe sampling itself. It will sample itself and start moving in random directions. So to avoid that, it's better to keep the sensor length a little bit high. Now too high sensor length will start having more like nonsensical behaviors. For example, if a particle is, say, at this particular position in like at my mouse cursor, and it's trying to sample points from this distance with a very high sensor length, well, it will give nonsensical behavior, right? So it's something I have to like tweak the parameters until we get something more reasonable. For sensor angle, if we just keep on increasing the sensor angle, we can see that it will, like, the field of view of the particle will increase, and it might like, in simple terms, it will gain the ability to look behind, right? So it will be able to look behind, so it will be able to turn back, right? So we can see more complicated behavior. Now in case of turning back, and with that behavior, what we can say is that the particle will start forming flocks, right? So if I just increase the angle field of view, you can see the particles are starting to form flocks, right? Particles are starting to be together. Now if I just decrease the field of view, now it's 400 right now, it's too huge. If I decrease the field of view, you can see particles are starting to move in more straight directions, and it's trying to like be more independent, right? Less flocking behavior. If I just make it very low, if I make the field of view, say something like, currently it's 100 degree. Now as I keep on reducing the field of view, you can see we are getting random behavior. Now negative is no good either. Now at 0 field of view, you can see a completely random behavior. Now yeah, how do I say random behavior? Well, the position of the particles are clamped between to keep them on screen, so you can see the particles at the end of the screen, but actually they're quite, as you can see, it's quite random behavior, right? If I just increase the field of view to something like 45 degree, you can see they start making some sense, yet they're not very not very interesting. But if I just increase it to something like 180 degrees, you can see more interesting behavior starts showing up, right? Now I can reset the positions, and you can see more interesting patterns are being formed. Now I can tweak the different values again to get different behaviors. Now one more interesting thing is that, like, we are seeing all this. Now how can we use it to our in some real life scenarios, right? That is the most important part. So I'll give you a simple example in this video, that is pathfinding, right? Now suppose we want to find the path from this town to this town to this town to this town, and all the towns, the classic traveling salesman problem. So we can just let this simulation run with various configurations and tweak the parameters, and we can just try to find the particle which has the say least which is like, based on our conditions we can evaluate the path traveled by each particle, and we'll check whether the path is good or not. We can find nice paths, right? Now, one more thing is that pathfinding in general case scenarios, like for example we have got obstacles, right? So we want to find the path from point A to point B, so we can do that too. Let me just add an obstacle out here and check show that to you right now. How can we add that? Well, let me just go ahead and explain the code a bit, right? So mostly the thing happens in compute shaders. Now this is I'm using my own library called CGL out here. You can check it out. It's open source. So okay, so what exactly is happening is how are we updating the particles? So we are taking the particle and getting up at every step. At every step we are getting a new direction for the particle based on the position and the previous and the direction of the particle. The direction of this particle we're calculating it by, well, the target town, the town the particle is trying to move to. We're calculating a vector from that from that point to the town the particle is trying to move to, and we are calculating the direction of that by normalizing that vector, and we're getting the direction, and we're trying to find the new direction based on that. This particle.extra0.xyz is nothing but the species or the genotype I was mentioning, or basically the color. Now this is called a mask. Okay, now how does get new direction function work? It's quite simple. We are just saying that firstly our default direction is in the opposite direction of from which it came from. Okay, so I just have steps. I'll just sweep through the particular area. For example, if I just open up paint, I can say that for example, let's say a particle is like this. This is our particle's line. Now I'll just this is our particle's direction, main direction, right? This is a particle's main direction. The direction we are feeding to this particular get new direction function is the indirection. Now, so this is the indirection. So this will be the FOVs. The FOV is, say, we've got a sensor FOV. Now we are moving from minus FOV by 2 to FOV by 2. That would be something like, say, this angle out here. So this angle out here would be this angle will be FOV by 2, and this angle will be FOV by 2 again. So we are moving from this to this, and we are basically what we are doing is, say I've got a line from this particle to this, and we are basically sweeping like this and sampling at every point, right? Now we have got steps, and we are basically sweeping out here. Now, and the distance, the distance of this line, let me just change the color to something like red. This red I chose. All right, the distance of this red line is the sensor length. So if the sensor length is very low, it will just try sampling points in very near. So as I said, if it is very low, it will try sampling the particle's own points itself, and what will happen in that case is it will just it will not have any particular direction to move to, because every single direction will be quite similar, right? So it will start showing random behavior. Also, if I just make it too high, too large, it will start sampling points that are not really relevant to that particular particle, and again it will show undefined behavior. We have to create tweak the parameters in a way to find the ideal length of the sensor to keep the particle to form really nice looking paths, right? Okay, now this is the sensor length. What about the sensor area? So this is the sensor length. The sensor area is something like a rectangle again. Rectangle. Now we are just sampling every single point inside this rectangle. This is the sensor. The size of the rectangle is sensor size, and we are sampling every single point inside this particular rectangle. That is a sensor length. Now, what happens whenever FOV is very high? Suppose rather than this line, the FOV becomes this line. What will happen in that case is, well, the particle will be able to look back, right? For example, the particle will be able to look behind, so the particle's new direction might become something in particle's new direction might be something in this direction, and the particle might be able to move behind, right? So that's not something we want most of the times, because we are trying to create paths, so it's not ideal for the particle to move in the opposite direction. But however, sometimes that behavior is required. Why? That behavior will help the particle to avoid obstacles in some cases. For example, let's say I've got an obstacle out here. Let's mark it with yellow, green, yellow now, or rather green, because it will be more visible. Now a particle is moving, say, in this direction. Again, black. A particle is moving in, say, this direction. Now if our FOV is something like this, okay, if FOV is something like this, the particle might not be able to find any suitable position, right? Because all of them are inside this block and no position is exactly suitable. In such scenarios, if our FOV is bigger, like it has the scope of looking back, particle might move in this direction and eventually move through this gap out here. So that's a benefit of keeping the FOV big. Now again, you have, as I said, you have to tweak these parameters based on how you exactly want your simulation to behave, right? So this is one more thing. The next thing I want to talk about is the let's say get back to the code and see what is the next thing out there. So we are creating the direction. Based on that, we are rotating. Now again, why are we doing this complicated? What is this complicated line of code, right? What is this complicated line of code? This is nothing but rotating a 2D vector along an angle. You can write it in proper like matrix, multiplying a matrix, the rotation matrix with direction. But again, I just avoided that and just wrote the entire formula, just like multiplied it manually and wrote that out. So this is basically rotating this in direction out here. This is rotating this in direction with a angle of theta, right? With the angle of this rotating this in the direction with an angle of our the current angle we are sweeping at. So this is I times step length, sensor step length, that is the amount we're covering in each step, because we can't really create a continuous sweep. In computer science, everything is discrete. So again, that's simple. Now we are rotating that vector and creating that, and having we are sampling that sensor data at that particular point. The sensor, how is this sampling sensor data done? I'll be talking about that a bit later. Once we sample the sensor data, we create the dot product between that. So this is a different thing. Just ignore this line for now. Okay, so we we check with the sensor data if the sensor data is greater than the maximum sensor data, and just ignore these two lines for now, right? So if the sensor data is greater than the maximum sensor data and the sensor data is greater than -10, well, again, this is what will be helpful for things like avoiding obstacles. We are just setting the new direction to be that direction. It's just finding out the direction in which the sensor data will be maximum, right? Again, one more thing, that is now back to this dot product of the direction and the indirection. What is that? Well, we are trying to find the dot product between the direction and the direction we are calculating and the direction inputted to us. What is that? Well, again, back to the MS Paint. Suppose after calculating all that stuff, our slime finds that this vector is the most suitable for is one of the vectors, or rather is one of the vectors that is available for it to go, right? Now what it will do is finding the dot product of these two vectors. What does that mean? Finding the dot product of this vector and this vector. Well, finding the dot product of two vectors means that it's a rough scale of how similar those two vectors are, right? For example, if the dot product of two vectors are 1, the vectors are equal, or rather in the same direction, right? And if the dot product of two vectors is -1, they are in opposite direction. Now for our case, we can say that if the two vectors are close to each other, the angle between these two vectors is less. If that is less, the dot product's value will be high, right? because dot product is the magnitude of both vectors, but most vectors have magnitude of 1 out here because they are directions and they are unit vectors. So both vectors will have dot product, magnitude 1, so the value of the dot product will be essentially cos theta of the angle between them, where theta is the angle between them, right? So if the angle is low, theta's value will be high. So if the vectors are close to each other, the value of cos theta will be high. So we can say that we get a rough measure of how close the vectors are. So what this does is we get that if the dot product of the vector is high, that is, if the vectors are close, it will be high, and if the vectors are far away, it will be low. In that case, we also interpolate that particular factor, that is, we use that as a factor, interpolate with that factor with our sensor data by a very small amount, that is 0.1. We can increase that. What this does is essentially, apart from moving along with our slime simulation logic, that is, like the slime simulation logic, as I said, is quite similar to this blog out here. You can check it out. Now we are just trying to force the particle to move towards the next town, right? This direction in direction is towards the next town, so we are also forcing the particle to move towards the next town. So that's adding a factor to that. So with that factor, we can choose we are choosing the new direction, right? So if we increase this to say something like 1, it will forget the slime simulation and start moving from one town to the other in straight paths. However, we are mixing it, so we are getting some interesting pathways, also forcing the particle to move from one town to the other, right? Now get sensor, this is the most interesting function, I would say, one of the most interesting functions out there. Now what get sensor does is, as I said, it samples the point in the map. So let's go back to that. Okay, so we are getting the position of the sensor. So again, as I said, direction times sensor length plus position. As I said, this is the position, so this particular point is the position of the sensor. This particular point is the position of the sensor. So let me just increase the brush length a bit. Okay, this particular point is the position of the sensor. Suppose direction plus direction times sensor length plus position will be giving us the new point, that is the final sensor, the point at which we are to probe the sensor point, the pos variable out there. So at that position, we are trying to sample it. How we are sampling it? Well, we have got a sensor size. Now it's an uniform variable we are taking in as input. Now also, what is the mask value? Mask is again the genotype or the phenotype or the color of the species. Again, it's an interesting way. We are creating a vector out of that. Okay, so how is this working? Well, it's quite similar. We are just moving in that particular grid. Okay, that block out here, this red box out here. We're moving in that box, or rather square or rectangle. This is a square out here. And then we are sampling at each point. Now I would say ignore these commented lines, we'll be coming back to those a bit later. Now we are just moving in that particular box or rather square and sampling points in there from this density map or the whatever we call it, and then we are just creating a dot product of that and the mask. Well, again, what is that doing? It's interesting. Well, we are having that particular point, we are creating a dot product with the mask. And the mask is again a vector, and this color out here is the species out here is also a vector. Now, what does dot product do? Just now we discussed that a dot product is kind of a rough measure of how similar two vectors are. So how do we don't really check whether the two species are equal, because that would be inefficient with a GPU on a GPU. Because alright, we are just running everything on the GPU because working for millions of particles, or rather on my computer I can run about 100,000 particles or 200,000 particles. Well, doing that on the CPU would be very slow and literally very impractical to do. So we're doing it on the GPU. So here I'm just calculating a dot product with that. So again, we're checking how similar those two are. For example, the density of the slime at that particular point, if that's similar to the density, the current species, then we'll try to move, prefer to move in that particular direction, right? So we're calculating that particular. That is exactly what our sensor data is, right? We're calculating that, and we're just moving in that direction. So if I just go ahead and see that once again, okay, so if I just add another town, you can see it's moving between the towns. Okay, let's go back to the center. Okay, now you can see the behavior is not very interesting. It's quite absurd behavior. If I just add another town and add the particles out there, see the behavior is not very interesting and quite absurd, because our parameters are not very well set up. If I just set up the parameters a bit well, we can start seeing more interesting patterns being like rising up. Also, I can again tweaking the parameter is something you should try out. Again, adding a lot of particles, a lot of towns, and if I just set up all of them, let's say, yeah, this would be a nice position. Now, if I just reduce the, the angle a bit, we can see things like it's starting to form parts, nice little parts, and moving on. Now, to add to this, what if I add an obstacle out here in the particles way? As I said, I was talking about path finding, right? Also, you can see it's starting to form paths, right? It's if you follow a particular particle, it will connect all the particular towns out there and form a path in its own. Also, it will do that while avoiding all the other particles because of what our mask logic is. Also, we can see at some points if some particles are trying to hold back other particles in a particular loop. For example, you could see a blue spot out here, right? Now, what if, again, back to the topic, adding a particular block to the particle again out here. So these three lines are basically for that. Now, the first two lines are not really that important. It's just converting the UV, the position on the particular map, from is like 0 to the texture size to -1 to 1. Like, we're getting a normalized size. Like, it will be easy for us to like relate to or calculate. So I'm just creating a square again, a rectangle out here. So let me just erase everything. So I'd say I have a rectangle out here. Okay, let me see the points. So minus 0.1 in the x and minus 0.1, minus 0.2 in the y, and my 0.1 in the x to 0.2 in the y. So if I just say this point would be minus 0.1 and minus 0.2, this point would be 0.1 and 0.2. Like, we've got this block out here, and the particle, if our sample, we are trying to sample positions in this particle, in this point, you will see the sensor data minus a huge sum, like 100. Why? Well, this will mean that at this position, the particle should obviously avoid this position, right? This is not a very favorable position. If we have a positive value, if we have a high value, it's a favorable position. This is the favorability. Now, if we have very low value, say minus 100, it's not a favorable position, right? So, and we can see that if the sensor data is less than minus 10, we can tweak these values again to suit our needs. It will just avoid that position completely, right? So that is what we are trying to say, is that our sensor data, our sensor is very it's very low out there. The point at that position is very low, and we should obviously avoid it. So if we just do nothing and just compile it and try and see what exactly this is showing. Okay, so again, again with one town, nothing should be more clear enough. Okay, now with one town I can show one more thing. That is okay. Now if I just move it to the center, we have got our block in the center, right? So if I just move it at the center, okay, and if I just increase the number of towns, yeah, you can see, okay, there is a bug. I have to say this is negative direction, right? Because it's moving in the same direction. Okay, now this should be direction equals to direction, and okay, minus direction, and this should be minus out here, sorry, in out here. Oops, that's a bit of an issue. Okay, now that's fine. Now it's fine. Alright, so what I tweaked out there is, when the particles were trying to move into that, well, previously it was just, if everything was less than 100, like everything was less than 10, minus 10, it was just going in the direction it was going originally, so it was just going through the obstacle. So I just forgot about that. So now you can see particles are trying to avoid the obstacle and trying to reach the town at the same time, and you can see it's creating some weird behavior, right? Again, as I said, if I just increase the factors, right now, if I just increase the town to 2, you can see the particles are avoiding that particular obstacle as well as moving from one town to the other, right? We have found like a simple solution to pathfinding using agents. This is a simple solution to pathfinding using agents. No algorithm has been applied, like no fancy algorithm like A star or in the breadth first search or anything. No algorithm has been applied. You're just having simple agents, like move around with simple rules, and that same system is like finding a path from this to this point to this point without using any particular algorithm in general. They are not aware of any particular algorithm. They are not even aware of that particular obstacle. They are the only thing they know is that at a particular particle level, the only thing they know is that that particular area is unfavorable, not very favorable for them, right? If we just increase that, or rather have different species, you can see they're trying to avoid each other too, and it's creating an interesting behavior, right? If I just increase the number of species towns and have a large number of towns, right? Okay, and if I just tweak the parameters a bit, okay, you can see you get chaotic behavior and all of so many interesting things, but all of them are trying to avoid this particular area. Now some particles are moving in through the area, but again we can just ignore one or two particles, right? We can just add a safety check to just delete all of the kill the particle, kill this line if it enters that position, and still you can see avoiding all of the particle paths. We are still finding different like nice paths from one town to the other. Now we can add more obstacles to it by just simply adding to this line. Now this is not a very easy good way to add obstacles. There are obviously better methods, but obviously for simplicity's sake I'll be using this, right? Again, let me just add a few obstacles. Okay, so I added a few more, 2 more obstacles. Now let's just see how they work. Okay. Alright, we've got a particle out here. Let's just have more towns, right? That will be more interesting. Let's just have random particles, right? Okay. More towns would be better. Okay. Now, tweaking the things a bit. Okay, so you can see it's avoiding all the obstacles as well as getting from one position to the other without any issues, right? This is an obstacle out here, as we can see. This is one, there are 3 out there, and it's really avoiding all of them and like moving from one position to other. Now you can see one more thing, that if I just move the particle in a particular move one town in a particular way that it has no other way to go to that particular town, you can see the particles of different species start flocking out here, because it is not able to reach that. And you can see the like it was supposed to go from one town to the other, and likewise, but since all the particles can't really reach this town, so everybody is stuck out here, right? So everybody is stuck right out here. Now if I just increase this, and if I just increase different parameters, I can have different behaviors out here. If I just make the now again, one more behavior I want to show is that, see, currently if you see the sensor angle, it's less than 180 degrees, so it can only look in the forward direction. So as I said in the example while drawing in the paint, you can see it's stuck, right? It's stuck. However, if I just increase the moment, you just look at it, the moment the sensor angle is going above 180 degrees, it's starting to move in other directions too. Because it's trying to avoid the particles of other species, so it's starting to move in other directions too. If I just make it 360 degree, you can see quite interesting behavior starts showing up, right? You can see previously all the particles of different species were clogging together, but now different species particles are starting to form flocks and moving apart from other species particles. Now if I just move this out here, you can see it's going there and like instantly going to the other towns, right? Again, we can see interesting behavior out there, right? This is one of the interesting things we can see. Now, apart from these pathfinding, also it has various use cases. You can look them up, like slime simulation use cases, right? Now, you can see this town has no visitors right now. They will be coming. Yeah, they came right now. You can see we can add obstacles. We can say create a path. Now I'm not going to do it right now, but we can just create a path like this and say the particles can only move in that path, right? Also, or rather, particles cannot move in that path, creating a wall, right? That we can create interesting things. Also, apart from all these, this looks cool. It looks so cool, right? Okay, now next behavior I want to talk about is, now currently the particles are moving from one town to the other. Now what if I tweak that and try to make something different? So what if I change that and okay, I'm just right, sorry, yeah, right. In the currently whenever the particle is reaching the position, it's trying to move from that town to the next town. However, what if we try to move back to the same town, right? Moving from town A to town B, again back to town B A, like continuing that forever. How will that look like? Like what I expect to see is, let me just tell it in advance, is formation of more clear pathways, right? Okay, now sadly enough, our town has been initialized inside the barrier. Okay, now again one more behavior I would like to point out. Currently the field of view again is less than 180 degrees. Again, it's stuck. It can't come back to its position. The pathfinding behavior is like failed at that particular point. So again, how to overcome that? We can just increase the field of view. The moment it will reach more than 180 degrees, it's 170. You see, just the moment it will reach 180 degrees, it will start moving in different directions and coming back, right? See, some particles are starting to come back. Again, if one comes back, other follows, right? If one comes back, other follows. If I just increase the sensor length, again, it just obviously, yeah. Okay, if I increase the sensor length, again, it will start to be showing random behavior and follow. I can just say, okay, now one more thing is, okay, let's just add more towns. Okay, 2 towns should be enough. Okay, randomize that. Currently, you can see particles are moving from one town to the other and back to the same town, right? Okay, I just this line shouldn't be commented out. Okay. Alright, so 2 towns. Okay, let's make it a bit distant. Okay, particles are moving from one town to the other and coming back to the same town. Quite an interesting behavior, not very interesting. Now if I just change the parameters again a bit, you can see create interesting patterns. Create interesting patterns, and again, if we just reset it, different species out there. Okay, let's just add more towns. Let's see that. Let's add way more towns, right? We want something interesting. Okay, let's just try and arrange them. You could play around and like arranging these and creating different patterns out there. Okay, now I've got this particular out here. Now if I just say increase the sensor length a bit, decrease the center angle to the point where they can only move in one direction. Now you can see as the center angle reduces, they can only move in one direction, they can only look in one direction, particles start moving quite straight way. However, if I increase the center angle and reset the position, particles start showing more random behavior, right? Now I need to increase the center angle. It's 42 degrees, is way too low. Say something like okay, yeah, I guess something like this should be okay enough. Okay, sensor length is bit okay. I'm just resetting the positions and we can see different behaviors. Now one more thing I can show is I just want to randomize the position of particle slightly at every turn. So like, you know, the particles not only move in according to the particular position it's supposed to go, but also in a slightly random way, right? If I just increase the randomness a bit, you can see more interesting things arise. More interesting things starts arising, right? They are not only moving in particular ways following the following the other particles, but also in more random ways. So more as we increase the randomness, if at a certain point it's just boom, everything blows out again, something everything comes back if we just decrease the randomness. If we just increase this sensor length, and like if we have to, the main thing in this thing is you have to adjust the parameters to get things right. Once it's right, you can get really beautiful looking patterns. Alright, so well, you can see again it's starting to form paths and moving back and forth from one particles. Now this is not having any visitors, because you can see the visitors of this particular town is being blocked out by the green particles because they are more in number. If I just move this town out here, whichever it is, okay, whatever. Alright, so again, let's see that. If I let me just increase the number of towns to more. Reset that. Alright, we can see beautiful behavior again. Alright, so well, we can see particles moving and starting to form paths again. Alright, so that's it. Now you can obviously tweak several things out here, like the color of the particle. Now initially how am I setting the genotype of the particle? Currently I'm setting the genotype based on the starting town. Now you could do something like completely random genotype. So if you do a completely random, each particle will have a completely random genotype. Let's just try that, right? Let's just try that. Okay, let's just try that. So rather than this, we can just say each particle will have a completely random genotype, and it will be unique to that particular particle. So like in that way we can see some different behavior. Alright, so everything will be grayscale right now. So let me just increase the number of towns. Okay, yeah, the obstacle is still there. Now it's starting to look like more like the blog, right? Okay, since now there are different species out there still, but I am making every single one of them grayscale. Let's just increase the town to something more drastic, and we can see more interesting things starting to pop up again. You can see different particles trying to avoid each other, the obstacles, as well as trying to move from one position to the other. Okay, more towns, more the fun. Let me just increase the angle, field of view, more something more. Okay, now we can see we're trying to get paths from one town to the other. Like one particle is moving from this town to this town, like this town to this town and back to this town, right? So we are getting a path from this town to this town, a valid path. From this town to those town, we are getting a path. Again, we are getting paths from one town to the other, right? We are getting also different paths, like different routes are getting mixed up, and we are getting this kind of a path. What if now an interesting question? What if I make every single particle the same species? Okay, what if I make every single particle the same species? What will happen in that case, right? Everything is say 1.0. everything is the same species. Now we will be seeing some interesting behavior which will be quite similar to this blog, I guess. Okay, let's see that. Okay, with one particle, nothing much to say. With two particles, again, sadly our point is inside that. Okay, again inside an obstacle. Again, it's I have to increase the field of view above 180 degrees. Okay. Okay. Right. Increase the randomness a bit more. Now increase the number of towns. And now if I just reset it, now you can see it's starting to form paths again. If I decrease the field of view again, okay, and increase the length of the path probe, you can see it's starting to form paths, and you can see clear paths from one town to the other, right? With a negative field length, it will be quite weird. If I just increase it again, okay, well, it will start forming paths quite soon. Alright, so we can see again the paths are being formed. Now it's just from one town to the other, back and forth version, right? If I just go ahead and switch back to the previous version where we just were going from one town to the other and like cycling through them, we can see some more behavior, interesting behavior. Okay. Alright, so sadly again everything is inside, it's initialized inside the block. Okay, that's good, that's better. Let's increase the number of particles. Okay, from this point to this point, and we can see it's starting to move in clear directions from one point to the other. Now again the defaults are not really cool enough. Okay, now let's just have more towns. Okay, randomized. You can see we're starting to get paths which we could use as roads between these towns, right? We can follow these, and we're getting quite efficient roads, right? Like I won't comment on the efficiency just like that. You have to calculate the things actually for finding out that, but we can see that it's starting to form roads, like connecting paths between all the points, right? Okay. Now if I just now it's too mundane. If you feel that it's too mundane, also we could like change the positions of each particle out here. Now it will come back. Yeah. So if I just change the positions a bit, I can tweak the path to my liking. Okay. The angle, if it is too high, you can change it. The path length, you can change it. Okay, the angle is too high. The path length is too high. Okay. Now we can create paths. Now what if the system gets settled and it's too mundane? We can add some randomness, right? We can add some randomness. Now each time the particle is moving towards the position, it's also getting some random velocity. So it's just having some random behavior too, right? We can simulate a lot of behaviors with this simple set of rules, right? Right, so you can now it's up to you to what you do with this. For example, whether you can have a new system in which how you're assigning the genes to particular particle. Now you can have a different system on how you're assigning the positions of the parts, or how you're trying to like calculate the favorability of the particular direction. There can be several updates on top of this. So well, that's it for this video. Thanks for watching.